Alrighty then, let's get started. We're going to think about making an estimate. And what's the estimate about? The estimate's going to be about how long would it take the natural global system to clear out the pulse or plug or slug of CO2 that we're putting into the atmosphere. We'll refine that estimate, but that's a major objective of this particular exercise, this particular unit, excuse me. I'm going to review some things, and your assignment's basically going to be working in that same model that you played with. We're going to, though, instead of just describing what you see, we're going to ask you why. So that'll be a little more amusing, and we're going to have you play with what we call turning the knobs. Most models have all kinds of variables in them, and if you change the variables a little bit, you get different results. And so the modeling beauty of it is that you can twist the knobs to your heart's content. So I'm going to let you twist some knobs because surely it'll content your hearts. And that's going to be in the big cycle, and then we'll put it to practice. I'm going to introduce a concept that we'll delve into a little bit deeper Tuesday, but it's basically the concept of peak carbon. And we'll see what that is when I get that far. Before I go anywhere, questions from you folks? All right. It came up, there's a lot of folks having challenges with issues of getting homework in lately. What I've normally done, please let me know that you're going to be missing or something, and I'll tell you to put the assignment, to email me the assignment. It's a real pain to have you upload it on Canvas, but if you miss it, then we can work with it that way, okay? I want to talk about this gradient business, this diffusion, this notion of things moving out and they change the rate based on the change of the concentration. So this diagram here shows the notion that if you have things clustered together, they're going to move apart at a certain rate. But the further they get apart, the slower that rate will go. And that's this exponential curve that we've talked about. I just said it a little differently than I've said it before. Don't worry about the fancy formula, just the notion that there's sort of gradients. There are things that drive things in the natural world, and most of them have some sort of exponential function to it. One of the things about an exponential function is that it doesn't actually get to a certain value. You know, a linear curve will cross a certain value. Something that is coming like this will get closer and closer and closer and closer and closer and closer, but not quite make it. Asymptotical, they call it a little bit. So the notion is you could get from here to here pretty quick, but if you wanted these all perfectly, so you're going from here to here, say, if you wanted them all perfectly diffused, it's like way over there on the timeline someplace. All right, so that's a concept. Another example, because I think this is so important, two examples actually. One is, if you think about a water filter, if you push water, trying to push water through that works fine. The more you push through it, the more water will come out of it. So there's a change in the rate of it based on how much pressure that you put into it. The water is capable, the filter is capable of moving stuff through it, that's fine. But it depends on how hard you're pushing it. So that pressure is a little different than the water levels we had in the example boxes that we made, because that was always under the same pressure. Another example is kind of like the last slide. If you put a concentration of eyedroppers in your water, you know, the food coloring or something like that, it would start off as very concentrated drops here, and then it would slowly diffuse to this fashion. Now the rhetorical question I have at this, so everybody sees the dye of the food coloring or whatever versus the water molecules. But there's a series of lines here, they're not all quite the same, and I'm trying to explore what the difference between these. So if I could do the experiment hypothetically with one drop. I could do it with 10 drops. So, lady with the cylinder, small cylinder, which is more representative of a 10-drop situation? This curve or this? This is a family of curves where basically we're going to see the concentrations difference. Do you think is it going to be a high one or is it going to be a low one? It's going to be the high one because I've got more stuff in there, so there's going to be the impetus for it to move apart more. The one little drop doesn't really have the pizzazz in some fashion. I mean, that's not quite the right physics, but to do anything. So the one drop will take a while longer in here. So it depends on, again, the water level or the pressure or the gradient. And that's a good concept to keep in mind. Now, I want to revisit the bathtub model again because I realized in retrospect that the way it was set up might have been ambiguous. Probably was ambiguous would be a better way to say it. And I want to set it up slightly differently and basically as a different example. So one way to interpret this diagram is that the water level keeps dropping. Another way to interpret it is this is the starting point, this is the starting point, this is the starting point, and this is a different starting point. So you could interpret this diagram either way, and I didn't make any differentiation in terms of evaluation. But I want to do the exercise where those are 4 separate diagrams. 4 separate diagrams, different water levels to start, same amount in. Now, what's the resulting out in this case? That's a colorful one of those things. What's the sort of the physical processes here? I'm starting all the same in, but my difference in starting is that I've got 4 different water levels. What is the pattern of those imply?
The higher the water level is at the start, the higher the pressure will be when you add more, so more will flow out faster. If you're closer to empty, you won't get forced out as much.
That's not necessarily a very viable physical situation, but that's the correct interpretation. So this is the business where if you don't have a lot of water, it can't go out. The filters, well, not the filter analog. More water, more it goes out. In this case, the pressure out's going to be equal. This case, it's opening up, and there's really rip-roaring water. So you can get these conceptual relationships between a lot of processes where things are moving, or fluxes, or chemistry is moving among different particles. And so if we want to, and I think we should, I'm not going to ask for this one on the assignment, but let's sketch these out. Let's take a minute to be sure we can sketch those out. So this one, what would this one be? As this evolves over time, the water level, and there's the starting water level, what's going to happen with this case? Going to decrease, but the water in and the water out are the same, right? So it's going to stay the same, right? Okay, so that's a straight line across here. Now, this might be I'd actually, and if you squint just right, I've actually changed the water levels in each one of these. So you could have the pattern, but this is a clue that that's the line for that one. All right. What do you want to do with this one? What are we going to do with this as it evolves over time? Time is everything. Time axis on all these flows is a big deal.
It's going to decrease.
And is it going to decrease?
Exponentially, I think.
Okay, why?
Well, isn't this the one where you're pushing the water out?
Yeah, we're pushing the water out. We see a system where it has a nonlinear response.
So the more, in the beginning, if you push, more water's going to come out in the end.
That's the concept we're trying to get a hold of, yep. Any difference in this one? To this? Is it just how would this be different? How would these two be different? They're both more flow than goes in. They're at different levels, So I've got the sketch here. What about the resultant curve after as it evolves?
The first one will decrease faster, but yeah, it's not a straight line, it's a curved line.
It's an exponential line, and you're actually right, it'll go faster towards.
Yeah, I mean, if the rate is changed according to the level.
And then if you imagine that this rate does change according to the level, then it will taper off right there. And so if you talk about it totally asymptotically, then it keeps getting less and less as the water level's less. It's sort of longer and longer and longer and longer to finally get that last drop of water out of there. Okay. This is a kind of thing where the actual physical thing is not if you have a static water level to start, but you have a water level and then you dump a bucket in it. And we're going to dump a bucket of something into the atmosphere here pretty quick. And that we dumped buckets of water in last time, and we saw how they accommodated. We're going to get more analytical about it as we go. Any questions on this so far? Do you want another one of these pretty things to do? Or you're good on those? You're good on those, okay. What is this diagram, what is this sketch of, and why do we care? It's the carbon cycle, and what parts of the carbon cycle are we looking at so far? The fluxes, and remind me of the difference between fluxes and the pools.
Pools where the carbon's stored, the fluxes are the transition.
And you'll see some terminology where they'll talk about the pools as a reservoir, as a sink or source, or there's other terms, but that's where stuff is, conceptually stuff is stashed. What are some of the pools that we're worried about here?
Yes, fossil fuels, the atmosphere.
And so those are the blue numbers, and there's only about 3 or 4 of them in this particular diagram. Okay? Gentleman behind him, what are the red arrows?
The direction in which the whole chart is flowing.
And it's a flow, and in this case, it's a flow of what?
Carbon into the atmosphere.
Carbon into the atmosphere from this particular process. And what's the number? There's a number 1, this is a 0.1. Why do I have different numbers on the arrows?
Is it the amount of carbon that goes into the atmosphere?
It's the size of the, if you think of them as a fire hose, it's the size of the hose. So this is a tenth as much, it'll bring out a tenth as much carbon per unit time as this one will. And these are all sort of 100 times lower than these. Gentleman next to him, what's the implication for 2 fluxes sort of going between the same 2 pools but in different directions? Why would, excuse me? Not necessarily feedback. A feedback might regulate how those go, but a feedback wouldn't necessarily set up 2 fluxes. So there's 2 fluxes here. They're close, but not exactly the same. So which way would the CO2 accumulate in this system? In the atmosphere or in the surface of the ocean? Not much, because it's only 2 out of 90, right? But every year, if these are fluxes per year, and they are, then we're taking, and this is all that there was there, we're taking 750, a year later it would be 748, blah, blah, blah. Each year there would be 2. What do you think would happen as we get down to like 10 units in the air? Do you think we could still take out 2? Why not? Conceptually, it seems like it shouldn't go as fast with only 2 as with 750, right? All right. The other point, though, is those are different physical chemical processes. That's why the arrows operate both ways. It's not the same stuff going back and forth. This is an absorption of CO2 because the bugs in here the biota in there want the CO2, they take it out of they take it out of here, and if this gets too low, it'll suck up more from the adjacent. It's passing through the filter of the atmosphere. The atmosphere will suck up more. The loss is because you have things decaying in the ocean, and they give up CO2. Or you have things respiring in the ocean, so it gives up CO2. So the point is that a lot of systems that have two different arrows, there's different processes involved. And they may or may not, in this particular case, they're pretty close, but they may not always be close. All right, gentlemen way in back. What arrow about, what, any of these arrows don't make sense? Any particular set of arrows that don't seem like they make sense to you, or would you like explained further, or would you like me to ask you the right question so you can explain it? That's what I'm really after.
I'm surprised that the burial of sediments is so low.
You're surprised about this one. And by gosh, that's the smallest fire hose on the diagram, right? And why is that weird? There's got to be a smallest one. So what it means is the process is what? They take a long time. They're slow. But there's something else that's a little bizarre about this one. What's this big number here? 37,000. And that's like number 2 on the whole kit caboodle. None of the rest of these numbers are anywhere close to 37,000. So here's one of the biggest pools, sinks, sources of the carbon cycle, but only 0.001 are going out every year. If nothing else happened, how long would it take for that process to drain the deep ocean of its carbon? Well, it's a couple more zeros on this, so 2 more zeros would be 3.7 million years, yeah. Okay. How long have the oceans been around on this planet? Much longer than that. What does that imply? Some places more carbon being added. And we don't see it on this diagram. Fortunately, we'll see a more complicated diagram later today where it's included. But that's the natural conclusion you have to draw. Any part of this that you'd like to know about more? The burning of fossil fuels, okay? Is it a big number compared to, it's bigger than this one by a lot. It's still under 10. And is it a one-way street on this diagram? Yes, it is, right? It is. Because there's no, here the ocean's going back and forth, here there's some things going back and forth, and this one is, where does that come from? It's the dashed arrow on that, right? So the fossil fuels come out of the earth, and they are transmitted or utilized here and then expelled in the atmosphere. Why don't they just draw this arrow as the 0.9 from here? Why do you think they make a fancy arrow out of it? Nothing else has got a big fat arrow and then a little one, then 2 little ones. Did they have to do it that way? Why couldn't they have just drawn an arrow, one arrow? I don't know either, but they're actually trying to, because they're drawing 2 arrows, they're saying here's an activity, here's another activity that's contributing to this, basically the same net result. So these diagrams have a lot of information in them. They're a miserable thing to build. If you try to build one of these things, getting all the numbers to balance is not a trivial task. And people argue about these all the time. Any more we need from this one? Anybody else? Everybody's trying to hide so they won't get called on. All right, so this is this model. We're going to change our uptake about part of the assignment. No, the whole assignment is playing with this model today. And we should be cognizant that the oceans are pretty simple in this model. We're going to go to a more complicated model for next assignment, but not for today. And so this is a good thing because I think we can get our hands around it. But what I want you to do in here, there's two knobs that you can change. You can change one, you can change the rate of this arrow. And the other knob that you can rate is this one. So they're only giving you a chance to change two knobs instead of 10 or 20. Gentleman way in back with the, is it pink?
Red.
Red. Okay, with the red thingamabob. Why shouldn't they give us all of the knobs to turn?
I guess because like if you change them all, then you're not really sure how big of an impact.
You'd have no idea why something happened. So the conceptual thing of a model is to turn one knob at a time, see what its effects are. Your homework exercise is to turn this knob only. You could do the same thing with this if you wanted to, but I'm then going to have you examine, because by gosh, this thing doesn't just interface with this, there's linked effects. So in other words, we're going to see that this thing goes into the atmosphere, but the atmosphere, there's all kinds of ways for it to get in and out of the atmosphere. So we might expect that some of those will behave in different ways. And we should expect that because the numbers for each of these things are differently. So that's the homework, that's the assignment there. New topic, peak carbon. There was a very perceptive petroleum geologist a while ago, 50 years or so ago, and he recognized the conceptual problem, or a curiosity. And so here's 200 years in time, and this is the production in some volume of whatever it is, barrels or billions of barrels a year of oil. Oil per se is how we recognize this. I think it could apply to all fossil fuels. And this is what's happened in the past. And this goes back because he didn't discover this for quite a while ago. But then he sort of projected what he thought would be down to the future. And he did it in two ways. One is he said, okay, geologists, one of the big activities is to find new oil sources. It's a geological setting. So at some point you know how much more oil there is. You see the things where they want to open up a new resource and they'll say, oh, there's so many billion gallons here. Well, how do they know that? Well, somebody's done an investigation. So, and then you drill the ground and you can find out it is. So one thing is you used the oil. Another is that you have some reserves, proven reserves, what they call. They can establish, but from their individual studies, that there's so many more billion gallons. And then there's a concept here in yellow where he says the future discoveries. Well, it turns out that finding oil is almost, what he's arguing is the point of diminishing returns. That you can keep looking for oil, but as you keep getting more and more oil, or identified, or used, or whatever you want, you can't keep finding more oil. And so it decays in, an asymptotic way. So you could get more oil, but you can't, it's harder and harder to find. Once you've discovered it all, there's nothing left to do. So the conceptual idea here is that we can use oil, but the availability of reservoir, this has nothing to do with production just yet, is finite. Okay? So what do you suppose went into what things would go into this? This is how much we've used, so we knew there was that much. What would go into the notion of why would this curve crash and burn? we're gonna use more oil, that's absolutely right. Why would the amount of oil we use down the road change the amount that we could actually get out of the ground? This isn't use. There's a subtle difference between use. They kind of look the same. But if you wanted to use it, why would as we kept using it, why would the amount potentially you could get out of the ground keep going down? Because it's harder and harder and harder and harder and harder to find it, yeah. Because there's always going to be oil there. Part of the challenge is getting it out economically. So you could do this model for a economic value and say it's $100 a gallon. If you said, okay, but the oil's actually $200 a gallon, you'd have a lot more proven reserves. You'd have a lot more reserves you could get. Now, when you use it, it's gone. So this was a prediction about the production only. And he implied that it's going to drop off. You're going to drop off. The production in this case is by the end of your lifetimes, basically, year 2100, it'll be back to the values that we were doing in 1950. Okay, this curve has had a lot of influence and ramifications because now you can tweak the shape of the curve and the size of the curve and where you put the pretty colors, but conceptually I don't think anybody's argued against this. And the unit's in billions of barrels, and a barrel of oil is 42 gallons, so I mean it's a huge number. So this is the Hubbard curve, and it's the notion that we're going to run into peak carbon sometime. The amount of carbon that is available to us is going to crash and burn, or is going to go down, not crash and burn. Maybe crash and burn out here. So what's the ramifications if there's no more carbon to be had? How would that matter to sort of this concept of global warming? No more carbon to be had, or it was too expensive to get. Why would I care about that? If there's no more oil to be produced, what are we going to use for an energy source? The ramification is we can't use that, so we're going to have to use something else. So to the extent that this is right, if society wants to continue using energy, we got to find someplace else. We got to find something else. And people who, when he introduced this, they recognized that problem. And if you're an oil company, you started buying up a lot of land to have your proven reserves up, so you didn't have this problem for a while. If you were an environmentalist, you said, or if you were an alternative energy, you said, I got to start planning for however I'm going to do alternative energy because petroleum's not going to be available to us. So it's a pretty profound concept. It has an interesting corollary. And the corollary is something about the use of the resource. Here's the curve we just looked at. Here's the Mauna Loa data scaled the same way. And we see that there's a similar sort of behavior here. We haven't had the inflection point on this necessarily. But yes, there's another layer to this, and how much are we actually using? This is the result of the part that takes the trip. And this diagram's a bit old, but here's a conceptual idea of that curve. And here I didn't put the years on it. This is the year 2100. And so, 2010. So this is the lighter colored line is the actual production of oil. And it's a couple years old. But it followed the curve nicely for a while, and then it bumps back up. So why could it bounce back up? Why wouldn't it just keep going down? This is the theoretical idea. It's a lot shorter time scale than the other diagram. Here's the actual usage, and it follows it nicely. And then all of a sudden there's a break. And that break is sort of, well, it's a few years before you folks were born, basically. But any other thoughts? Why could all of a sudden the use go up? Did something change 20 years ago-ish, 25, 30 years ago? Just all of a sudden we're producing a lot more petroleum, so they had to.
Yeah,
That's when they started fracking. They changed the technology. They changed the way to get the oil out. And it became, before that, you didn't anticipate being able to get more oil out of a patch. By changing that technology, you were actually able to extract oil you couldn't get otherwise. So all of a sudden, the production went back up. Okay, that's good. Fracking is a, and so there's also a lot of these fluctuations of production have to do with economics. We're not using them so much because the price of oil is up, there's a war on, so the price goes up and the production goes down. But those are fairly minor blips in the grand scheme of things compared to the change in technology. So that's fine. So the production is useful to know, and we've got it sorted out. And then people are still worrying about this. And this article's a year old, but it's about the Ukraine war comes into demand here. And there's basically an argument that the IEA, which is the International Energy Association, and we'll see some of the more of their information, but says that we're going to hit, this peak's coming. You know, it was coming before, now we've exhausted the technology of fracking, and we're still going to get it. And so we're back to the conundrum of what are we going to do for energy? Not next week, but in the next decade-ish, or maybe even longer. If you worry, you follow environmental news, they're not talking about this. They're talking about cutting out the CO2 because it has impacts on the atmosphere. Rhetorically, why don't we just wait for the CO2 to run out? Burn it all up. Burn, baby, burn.
too many tipping points we probably would have passed by then from all the other lessons.
Oh, those are all modeling experiments, though.
Well,
No?
forget about 5 of them. One of them would probably cause something that would be
Something maybe. So here's a conundrum. The oil's going to run out. And at the same time, we're trying to stop its use, which is all fine. But the contradiction is what? It's energy. It's not oil. It's energy, right? What's going to replace the oil? Excuse me?
lithium.
Lithium's going to be, somebody's already drawn a curve about lithium resources? I'm sure they have. Yeah. Okay, so there's a lot of haboo about changing your energy source to solar and wind. Well, those have different resources that they need, so there's another problem. Do they have the same thing of the decrease? Well, maybe they could. All right, that's a little off track. I want to draw back to a more rhetorical question, because we've seen that the CO2 levels are going up. We've seen that we still have oil or fossil fuels that are possible to recover and utilize. We have not replaced our energy source in a significant way yet. It's much more advanced now than I thought 10 years ago, but that's okay. I'm pleasant to be surprised there. But we still have a geologic problem. This is why we're talking about this. Let's assume, for the sake of argument, that we removed all of the carbon. Worst case scenario, we got all of the carbon out of the rocks and we dumped it at the rate we're using, more or less, into the atmosphere. Okay. Based on this diagram, that one, I take and dump this all out, eliminate that. These stocks are going to go up. This one will keep exchanging with the ocean. This one will do something. This one will go up. But ultimately, look, this is a one-way arrow out of the system. So if we let Mother Nature do its thing in the process, how long will that take? that's the rhetorical question we're asking today. It's not rhetorical, it's a good exercise. So, there's political ramifications of this. We're going to cut out CO2 by a certain year. We'll see how well that works out. I'm not going to get into that. But let's assume, for the sake of argument, we burned it all up. How long to get through, work through the carbon cycle? And that's our bucket, that's our slug. We're going to model, not this assignment, it'll show up on the next one, but how long would it take for the planet to come back to those levels that fluctuate through the ice ages? And it would. If you take that one reservoir out and you throw it all out in a bucket, geologically, the planet will, that's insignificant time geologically, kind of long politically, but it's an interesting exercise to go through. So this is sort of this business on the conceptual side. So I'd like us to think about this one a little bit, because we have the same problem. Now we're going to dump a bunch of stuff in here and it's going to drain out. So this is the natural world, really. If you dump it in and you got a lot of it, you can get rid of it fast. But if you make these time slices, it gets slower and slower. Right? Everybody see that? Does that make perfect sense to you? How much slower? How would we find out? Do you think it's going to be on the next slide? Well, then you'd look on your PDF and you'll find out it's not on the next slide. But we could model it. We could use a set of computer simulations to model it. We know the processes and rates, and that's what we'll do. So this gives us, I mean, I don't think we have to belabor the point, but that's going to be exponential decay. How fast? Tens of years, centuries, thousands of years, hundreds of thousands of years, millions of years. That's where we want to go with that. What's your first guess? 10 years? 10,000 years? 10 million years?
Hard to say, probably big number,
A big number, yeah. Lots of zeros.
over 10,000.
Over 10,000. We're putting it back, we're taking it all out like in a century-ish. 0.001, yeah, okay. What we're going to find is that there's this complexity has a lot of control on this. And we'll dive into that deeper on the next Tuesday. All right, so that's fine. We've done that. Oh, we're going to dive into it now. We're going to use a more complicated model, not the one that we've been using for the next, down to get this problem, we've got to use something a little more sophistication. Why? Because there are a lot of other things in here, and particularly these are all the same things that we've talked about. There are slightly different numbers, we won't worry about that. But we see that there's far more detail in the ocean. Here's the 0.001, it's 0.2 here, and it's going to go down into this, that's fine. But we see a line here, a line there, a couple lines here, some lines there, and it becomes a far more tractable problem. So we need a little more sophisticated model with more knobs, more math in it. And we don't necessarily need to know, this diagram talks about the current amount plus the change. How much is it going to change? And this is that big number, but it's going to change a lot. Well, that's good. Here's the fossil fuel things. It's not going to change much because we're going to run out of fossil fuel. All right, where does that leave us? Just a pitch for the models, and that's what for what we're doing, we're getting a first order estimate. If you put more math to it, you'll get a second order. You'll get continually refining. And this is all the computer models in the marine ice sheet instability hypothesis are continued refinements. So they seem to think that you're getting better and better results. Sometimes you do and sometimes you don't. David Archer brought this, a fellow that's up at University of Chicago, brought this to life in a popular book. Well, it's been a while now, but the subtitle gives you a hint. Archer suggests that the thumbprint signal is sort of a long time. And he developed, not for oil necessarily, we're going to use methane, but it's the same, be the same principle. So we'll talk about methane, and so I want to talk a little bit about methane to set it up. Here's his model, blah, blah. He's got actually all kinds of models. We're going to pick one, and I want to consider methane, which is CH4. Well, why do I care about methane? That's not CO2, but it's got a C in it, right? CH4. And I'm concerned about methane. Let's see, who needs to tell me about methane? Gentleman in back, what do you know about methane? Way in back. What color is that? Red? What color?
Red.
Red, okay. I'm not seeing very well today. What color is methane? Yeah. Well, it's a gas. It's in the atmosphere. So it's clear basically. Yeah, okay. All right. So what do you know about methane? It's a gas. Yeah, all right.
It's harmful.
Harmful how? We know it's harmful because the press says it.
Yeah.
It doesn't have a very good press agent, by the way.
Like, I guess it does like similar things like the CO2. Like it keeps in the sun's radiation and everything in the atmosphere.
The drilling behind you, the hammering behind you drilled you out. Sorry, could you say that again, please?
It like traps the sun's radiation like CO2.
It's a greenhouse gas. It's a greenhouse gas, like carbon dioxide. Now, when we did the thing about the greenhouse gases, I think I had a slide with methane, but I didn't talk about it a lot. But methane gets a lot of press. Why? Is it more or less effective than CO2?
It's less.
Less?
Yeah.
They usually tout it as more effective, but they do it, there's an accounting trick that they do it. It's supposed to be more potent than CO2. One of the things with methane, though, is it oxidizes in the atmosphere. So it goes away by another process. And it doesn't take long to burn off methane, 7 years. While it's there, per box of methane and per box of CO2, the methane is more powerful, but it goes away fast. So which is more powerful? Well, that's an interesting question because the methane becomes CO2. So you move it from one box to another. And my box of water is less than either of those, but I always maintained that H2O was the most important greenhouse gas because there's so much more of it. All right, we're about ready to get out of here. No, there's methane. You're going to pick a set of values and we're going to tweak the knobs, that's fine. A little bit more about methane. You can pick numbers about methane in tons. This is from 10 years ago now. Yeah, basically, and there's fossil fuels are a methane. Natural gas is methane, basically. Agricultural, you hear cow farts are the thing that is generally attributed to a big deal. Burn biomass and swamp gas, or the swamp gas is the natural methane, the green one. There's other natural emissions from the trees, and then it goes back in because it burns up, and it's also consumed in the soils. So the paths of methane are complex like everything else. The lifetime is 7 years, but it's a high radiative forcing. All right, I want to get out of this. Here, we want to talk about deliverables, finally. Methane. Any questions on methane? That's mostly a setup for the next assignment, today. More important, the assignment looks like this. You got a lot of one-pointers in here. And an 11-pointer. Guess which one's going to be the hardest to deal with? What do you think? You want a whole series of one-pointers or one bigger? Excuse me? Well, but fortunately, this exercise has both. This is about running the model, make some observations. And I'm telling you, I'm being very specific about the settings of the model, so everybody should have the same result. Okay? So basically, you had the two easiest knobs to turn on here with the use of fossil fuel and so-called deforestation. They're a little slider bar on the lower right-hand side. And we left them at 0 for the sake of exercise. I don't want you messing around with the deforestation bars unless you want to do it on your own. But I want to think about the fossil fuels. And I want to keep jacking that up. 0, halfway up, 20, to the end. So one set of experiments is run the default, tell me what happens. Change it, increase the fuel consumption, see what happens. Repeat as necessary. So we're going to go from the lowest value to the highest value. They have it in the middle and high value here. And you should see some significant changes. And I've been fairly specific about what pools to look at. And it's generally the atmosphere and the ocean pools. That's where it's all at. Okay? And then the concluding thing is, well, why did they have different results for different use rates of CO2, of fossil fuel, excuse me. Use it a little bit, certain behavior. Different behavior. Different behavior, and the why. I would encourage you maybe to think about making a screenshot or sketching the graph or something, because you're dealing with two different properties in 3 cases. And if you don't really look at, to make a comparison, it's a lot easier to look at 2 graphs at the same time and compare them than it is to try to memorize them. Now, the way I draw it, they wouldn't be very comparable because sketching would be bad. All right, do we want to get started on that? I'm happy to, if anybody's going to stay and get started on it, we'll work through it. If not, we'll see you on Tuesday. Have a good weekend.